Okay. So talking continuity and behavior today, continuous functions have no breaks, gaps, or holes. And the idea is that you could, oh, Kate said it first. There it is. Yep. Thank you, Kate and Aiden. All right. No breaks, gaps, or holes. If it's continuous, you can trace the whole thing out with your pencil without picking up your pencil. So that's an easy way to judge if something is continuous. So for example, something that looks like this would be considered continuous. Anything like this, maybe we stop there and jump down here or something like that, that would be considered discontinuous. So when something is not continuous, there's 3 different types of discontinuity that we are going to talk about today. So the first one is called a removable discontinuity. Sometimes they also call this point discontinuity. You might have heard it said that way before. So a removable discontinuity might look something like this, where it's only discontinuous at one spot. This would be considered a removable discontinuity at x equals 3. You could also see it, other than this, you could see it written in a piecewise function, something like f of x equals x squared if x is greater than 0, or x if x is less than 0. So there's no value for when it's equal to 0. So this would be a removable discontinuity when x equals 0, since there is no value. For x equals 0. So there's our first type of discontinuity. The next one is one that we'll see a lot, especially with piecewise functions, called a jump discontinuity. And we'll switch colors for fun. Okay. So a jump discontinuity is when you would have to jump from one point in the function to the next, where you'd have to pick up your pencil to do so. So it could look something like that. And we might see this in the form of a function f of x equals 2 if x is less than or equal to 2, and 3 if x is greater than 2. So that would be considered a jump discontinuity there. And then the last one for today is an infinite discontinuity, or considered a discontinuity at infinity. Okay. So an infinite discontinuity would look something like this, where you have asymptotes. So it could be the function f of x equals 1 over x or something like that. So if I was, tracing out this function, I would have to, in order to get to the other part, I'd have to pick up my pencil to do so. There's an infinite discontinuity there. Anytime you see a discontinuity brought on by an asymptote, that's an infinite discontinuity. Okay, so those are our three types. And the main things that we want to be able to do with this is, one, be able to tell if a function is continuous or not. Two, be able to determine where a discontinuity exists, so what value of x it exists for. So like up here when we say there's a jump discontinuity here, we would say it's when x is equal to 2. Or up here when we've got a removable discontinuity in this graph, it's at x equals 3. Or here it's at x equals 0. And then down here, it's wherever the x value is of the asymptote. In this case, it's the y-axis, which is when x equals 0. So we'd say there's an infinite discontinuity at x equals 0. So those are things we want to be able to do. Determine if it's continuous or not, figure out where and what type of discontinuity we have. And that's pretty much it for what we need to be able to do with discontinuities. So any questions about discontinuity before we move on to end behavior? Okay. So end behavior here, we want to be able to tell what's happening at the ends of the functions as x goes to infinity or negative infinity. Okay, if you have them later, you think of them, say something. Okay, so end behavior. So basically, we want to know what's happening to the function as x goes to infinity or as x goes to negative infinity. Okay. And sometimes we also refer to it as right end behavior and left end behavior. So right end would be as x is going to positive infinity. Left end would be as x is going to negative infinity. So some notation that we'll have. As x goes to infinity, f of x goes to blank. Those are oftentimes the sort of question that we'll see. Or as x goes to negative infinity, f of x goes to blank. And you'll say, fill in the blank with what's happening to the function. So this is easiest, or most easily done by example here, or shown by example. So these are some types of situations we might see. This is probably the most generic. If we're asked to describe the end behavior of this graph, we're looking at the arrows here and what's going on. So we would start off with as x goes to infinity, and then as x goes to negative infinity. So the right end arrow is the positive infinity arrow. The left end arrow is the negative infinity arrow. And then we're just describing what's happening to the function. If the arrow is pointing up, then it's going up to positive infinity. If the arrow is pointing down, it's going down to negative infinity. If the arrow is approaching some other value, then that's where you start looking at maybe it has an asymptote or something like that. But in general, most often you're going to see things going off to infinity or going off to negative infinity. So in this particular case, the right arrow is going up, so it's going off to positive infinity. The left arrow is going down, so it's going down to negative infinity. That's our end behavior here. And that's really all we have to do to describe end behavior. As x goes to positive infinity, f of x goes to, and then wherever it's going. As x goes to negative infinity, f of x goes to, and then wherever the function is going. Okay. So some other cases that we might see. Maybe we have something like this. And we're asked to describe the end behavior. So for our right end, we'd set it up as x goes to infinity, because this is always x to infinity, and this way is always x to negative infinity. So the right end, x is going to infinity, f of x is going to negative infinity since that right arrow is pointing down. Left end, as x goes to negative infinity, f of x is also going to negative infinity since that arrow is pointing down as well. Okay. So those are some of the more basic situations that we see for end behavior. I'll show a couple with asymptotes now as well so that we can get a little practice with that too. And then that's pretty much all we've got for today. So another piece of paper here. We might even see something like this again that we saw on our examples with discontinuity. This was that function f of x equals 1 over x. And this has a lot more arrows in it than the previous two graphs have had. So whenever you're looking to describe the right end behavior or the x going to infinity end behavior, you're picking the farthest right arrow. So this is going to help us with our right end behavior. This arrow is going to help us with our left end behavior. And there's a couple ways you can think about this one. As x goes to infinity, you can think about it in terms of the graph. It sure looks like it's going to 0, right? Like as x goes to infinity, it looks like this thing's becoming nothing. You can also think about it in terms of the function itself. The bigger the number that I plug in for x, the bigger my denominator is getting. It's getting closer and closer and closer to 0. So that's another way you can think about it. But in this case, as x goes to infinity, f of x is going to 0. And then the same idea here on the left arrow. As x goes to negative infinity, f of x is also going to 0. Because the more negative I make this number, the same thing's happening. It's getting smaller and smaller and smaller and smaller and closer to 0. Just coming up from the negative side versus the positive side. So there's some end behavior with asymptotes there. Let's see. I think that's most of what we need here. Let me double check. Okay, we could do something like this. We'll do one more example with end behavior here where it's a little bit different. This time we'll do, I'm going to give us the function f of x equals 4x minus 5 over 6 minus x. Okay. So for this one, for our end behavior here, it's going to look a little bit different just because the graph is shifted around a little bit. So it's a lot like this, but it's moved around. So let's go look at what that looks like on Desmos. So we had 4x minus 5 over 6 minus x. We zoom out a bit, we see that it looks a lot like this right here. Okay, so there's clearly some kind of asymptote here that we're not quite reaching, right? So for as far as our end behavior goes here, there is an asymptote, but it's not 0. Zeros are usually easier to pick out. But in this case, notice how there's an x on the top of the function and there's an x on the bottom of the function. And it's the same power of x both times. So an easy way to figure out what our horizontal asymptote here is going to be, or what our end behavior is going to look like, is to pick the thing with the highest power of x on the top and on the bottom. And as x approaches infinity, f of x is going to approach the ratio of their coefficients here. So in this case, it's 4 over -1, which is -4. So that's probably the hardest type of end behavior question that you guys will see. But yeah, so that's an easy way to take care of that one, is to take, instead of just kind of guessing at it or looking at the table of values on the function, you can take the coefficient from the highest power of x on the top, coefficient from the highest power of x on the bottom, as long as those powers are the same. If those powers of x are different, then it will have, the function won't look like that. It'll look different. But anyway, so then also as x goes to -infinity, f of x is also going to -4. Okay, so that's pretty much everything about continuity for now, or continuity and end behavior for now. Our assignment today is going to be in IXL, and it will look like a lot of IXL sections, but they actually go pretty quickly because most of them are yes/no type questions, or easily fill in the blank kind of questions. So I'll click assign, and then we'll go through and look at what we're expecting on some of the different ones here. Kind of look at a few examples. So we have a couple of determine end behavior. We have a couple of continuity ones. So for end behavior, we have G2 and G3, and these are both under calculus. And a lot of these are just, it shows you where the asymptotes are. So as x goes to infinity, f of x, in this case, goes to -8, because that's where the asymptote is. I guess this is another notation that you'll also see. You'll sometimes see the limit as x goes to infinity, or the limit as x goes to -infinity. That means the same thing, like as we were talking about. As x goes to infinity, f of x goes to blank. So this is just using limit notation instead. Or on this one, this time we're going to -infinity. So we're looking at the left end behavior, and it looks like -1 is the asymptote here. So as x goes to -infinity, f of x is going to -1. This one, same idea. As x goes to infinity, f of x is going to -4. Okay, so it's wherever those asymptotes are. And then let's see, on the next section, we have determine end behavior of polynomial and rational functions. So on these ones, it's got symbols for infinity, it's got fractions and things like that, and that's going to deal a little bit more with the kind that we just did, where you're looking at just the function itself. You can graph it if you would like to, but in this case, it's helpful to think about what would happen if you plugged in, a really, really big number for x squared here. Well, it would get, the whole number here would get smaller and smaller and smaller and smaller as my denominator gets bigger, right? So this one is going to 0. Same idea here. As t goes to infinity, this denominator is getting bigger and bigger and bigger, which means the fraction is getting smaller and smaller. This one, though, as t gets bigger and bigger and bigger, it does have a negative out in front. So t is going to be going, or the function is going to be going to negative infinity because it has a negative out in front and this number is getting bigger and bigger. And it's not in the denominator. Okay, so that's how those ones are going to go with end behavior. Any questions in the moment about end behavior here? Okay, so as we go through those, if you do have questions or anything, or there's one that you want to work on with me, feel free to come back on and we can do that. Then we have identifying continuous versus discontinuous graphs. So is this function continuous? Yes, because I could trace the whole thing without picking up my pencil. Is this continuous? Yes, because I could trace the whole thing without picking up my pencil. Same idea here. Here's one that is not continuous, because to trace the whole thing, I would have to pick up my pencil and move down here. So that section should go pretty quick. Then we have determining continuity. So asking, is it continuous at a particular value of x? So you go over to where x is -5, and we notice that, yes, it is continuous there. And this one, you have to pay attention to where it's asking, because if it was asking for when x is -3, it's not continuous when x is -3, but at x equals +2, it is continuous. So careful with those. Okay, at 8, again, yes, it is continuous there. It's not continuous at 7. Come on, is it ever going to give me one where it's not continuous? There we go. At x equals 8, this graph is not continuous. Okay, so hopefully we get the idea on that one. And the last one, analyzing points of discontinuity using graphs. On a lot of these, you're just listing values where there's a discontinuity. So when x is 0 here, there is a discontinuity. You're writing it as a single value or a list of values separated by commas. So if there's more than one discontinuity, make sure you put comma and then the other values of x. All right, let's jump a level and see what else we get. Same kind of thing. Okay, this one's a little bit harder. At least it's got a discontinuity at 0 and at 6. Okay, where it has a discontinuity, jump a level again. All right, so this one, it gets a little bit different here. Write your answers a single value list or a single value or list of values separated by commas, and then it asks how many removable discontinuities it has. So this is where we're getting a little bit more into what type of discontinuity it's dealing with. So we've got one at -8, at -4, at +4, and at 9. So looking at which of these are removable discontinuities, that would be this one here, this one, and then this one. This one's not removable because it is a jump. That would be 3 removable discontinuities. Okay. Let me see how much harder that one gets before I say anything else. Okay. So here we go for our expectations for the assignment for today. you have these IXL sections. All of them are going to 80 except I4, we're going to go to 90. So I'll edit that really quick. I4, we're going to go to 90. Okay. Any questions before we get going on this here? Okay. If you do have questions, stick around. Otherwise, I will post the exit ticket towards the end of the period. Feel free to pop back on if you have questions, but otherwise you are free to go for the day.